Good morning, everyone, and welcome to today's presentation. I'm excited to have you here as we explore the important topic of fire protection facilities according to OISD 144. This is the first slide, serving as our cover, where we introduce the session. We'll be focusing on chapters 11 and 12 of OISD 144, which cover essential fire safety standards. Over the next few slides, we'll go through key requirements, best practices, and guidelines to ensure safety and compliance. Let's get started and dive into the details. Let's take a closer look at OISD 144, specifically chapters 11 and 12, which focus on fire protection facilities. It's crucial that fire protection facilities include proper firefighting access, meaning clear routes for fire services to reach the area quickly. We also need to ensure there are safe means of escape for personnel in case of a fire. Additionally, facilities should be segregated so that if a fire occurs in one area, it doesn't endanger adjacent facilities. Another key point is the use of heat detectors. These detectors are essential for the automatic activation of our medium-velocity water sprinkler systems. They need to be strategically placed to effectively detect fire early on. In areas without specific hazards, detectors should be installed evenly across the ceiling, with a maximum spacing of 3 meters inside the shed. This uniform placement ensures reliable coverage and quick response. We also have to identify and consider the single largest fire risk within the facility. Recognizing this helps us design our fire protection measures more effectively. Overall, these criteria are vital to creating a safe environment, aligning with our commitment to proactive fire safety management, and ensuring that all facilities are adequately protected against fire hazards. Let's delve into the fire water pumping requirements as outlined in OISD 144, chapters 11 and 12. When designing the medium velocity spray system, we base the water flow calculations on a minimum spray density of 10.2 liters per minute per square meter of the exposed surface or area to be cooled. Now, for LPG pumps or compressors, this density doubles to 20.4 liters per minute per square meter, reflecting the higher risk involved. Moving on to storage vessels, it's important to consider the aggregate surface area of all vessels within a 30-meter radius from the affected LPG vessel's periphery. This combined area is treated as a single risk, which influences the overall water flow requirements for firefighting. For sheds, the approach is slightly different. The shed can be divided into multiple zones, each served by an independent deluge system. The key here is that adjacent zones should stay operative around the fire zone, effectively acting as a single risk. The width of each zone should not be less than 10 meters, except for zones at either end of the shed. Since loading and unloading fingers do not store cylinders, their spray systems can be designed as separate zones with independent deluge valves, helping to optimize water use. Now, considering the tank lorry gantry, we consider up to 8 bays as a single risk area. To ensure effective coverage, at least 3 tiers of medium-velocity sprinklers and heat detectors are installed to cool the top, middle, and bottom sections of the tank lorry. Moreover, the spray system must also effectively cover the tires, manifold, and dish ends of tank lorries of various sizes, ensuring comprehensive protection. Finally, when we talk about flow rate design, the goal is to ensure that the water system can deliver adequate flow to cover all these elements efficiently. This involves understanding the risk areas, the surface areas involved, and designing a system that provides optimal coverage without excess. The key is to balance safety and efficiency, ensuring that every risk is adequately protected while optimizing resource use. Let's take a closer look at the LPG pump and compressor house. This entire area is considered a single risk zone, which simplifies the fire safety planning. However, it can also be divided into smaller zones, each at least 10 meters wide, to better manage fire risks and containment. Moving on to the tank wagon gantry, this structure can be split into multiple zones as well. Each zone should be at least 30 meters long, and importantly, Zones that are adjacent and operate near each other are treated as a single risk if they are around the same fire zone. This approach helps in effective fire protection and response planning. The spray system installed on the gantry is designed to cover the surface of the tank wagons on both sides, ensuring protection in at least 2 tiers of spray coverage. It also covers the LPG pipelines within the gantry, which are critical areas in case of a fire. Finally, the fire water system in the plant must be capable of handling the highest fire water flow requirement, which means it should be prepared to manage the largest single risk area at any given time. Additionally, it should supply 288 cubic meters per hour to operate 2 fire water monitors, or for supplementary hoses, ensuring we have robust fire suppression capability when needed. All these measures are essential to maintain safety and prevent escalation in case of an incident, aligning with our overall safety objectives for the plant. Let's now look at the fire water pressure system as outlined in OISD 144, Chapters 11 and 12. The system must be designed to maintain a minimum residual pressure of 7 kg/cm2g at the most remote point in the plant. This ensures that, even at the farthest locations, there is sufficient pressure to deliver water effectively during a fire emergency. Next, a fire water ring main is to be installed all around the perimeter of the LPG plant facilities. This ring main acts as a backbone for the fire water distribution network. Hydrants and monitors are to be spaced at intervals no more than 30 meters when measured aerially. This spacing ensures adequate coverage for fire fighting. It's important to note that fire hydrants and monitors should not be placed within 15 meters of the facilities or equipment they are meant to protect. This distance helps prevent potential damage to the firefighting equipment and ensures safety during operation. Moving on to the network design, the fire hydrant system should be configured in closed loops. This design allows for multi-directional flow, which is crucial during emergencies because water can be supplied from multiple directions, increasing reliability. Isolation valves must be incorporated into the network. These valves enable sections of the system to be shut off for maintenance or in case of damage without disrupting the entire network. Typically, these valves are located near loop junctions for easy access. Additionally, in segments where the pipeline length exceeds 300 meters, extra isolation valves should be installed. This helps manage flow and maintain pressure across longer distances, ensuring that the entire system remains operational and effective during a fire. Overall, these design principles are vital for creating a robust, reliable fire water system that can respond efficiently in emergency situations, supporting safety across the entire LPG plant. Let's talk about water storage for hydrant service. The water should be stored in easily accessible reservoirs, which can be surface, underground lined, or above ground tanks made of steel, concrete, or masonry. The key point here is that the capacity of these reservoirs, above the level of the suction point, must be at least enough to support 4 hours of the pump's combined working capacity. Now, if the make-up water supply system provides 50% or more of the total water, this storage capacity can be reduced to 3 hours of the pump's rated capacity. It's also interesting to note that large natural reservoirs, which have a water capacity exceeding 10 times the total water requirement of the fire pumps, may be left unlined. This helps in saving costs and makes use of natural formations when feasible. Moving on to the design of storage tanks and reservoirs, they should be divided into 2 interconnected compartments. This setup makes cleaning and repairs much easier, and specifically for steel tanks, there should be at least 2 tanks to ensure redundancy and reliability. Overall, the main goal is to ensure a reliable water supply for fire protection, with proper capacity, accessibility, and maintainability built into the system. Let's take a closer look at the fire water pump requirements as per OISD 144, Chapters 11 and 12. First, at least 1 standby fire water pump must be provided, and if there are up to 2 main pumps, a single standby pump is sufficient. However, for 3 or more main pumps, You need to have at least 2 standby pumps of the same capacity as the main pumps. An important feature is that these fire water pumps must have automatic starting facilities. This system should operate based on a specific logic, ensuring that even if the initial pump doesn't start or fails to build up the required pressure within 20 seconds, the standby pump can take over seamlessly. All fire water pumps, including the standby units, should be diesel engine driven for reliability. The pumps are designed to discharge at 150% of their rated capacity, but they must do so at a minimum of 65% of their rated head, ensuring they can deliver sufficient water pressure when needed. Each pump engine should have its own independent fuel tank, large enough to support 6 hours of continuous operation. This setup guarantees operational readiness during emergencies. The system pressure at the farthest hydrant point must be maintained at 7 kg per square centimeter gauge, and this pressure is stabilized automatically with the help of a jockey pump. The jockey pump starts and stops automatically, controlled by pressure switches, to maintain consistent pressure in the system. If the number of hydrant points exceeds 100, a standby jockey pump must be added to ensure pressure stability. Remember, for capacity calculations, one monitor is considered equivalent to 4 hydrant points. Finally, these fire water pumps are of the centrifugal type with flooded suction, which is ideal for ensuring efficient and reliable operation in emergency scenarios. This comprehensive setup ensures a robust and reliable fire water system, vital for safety and compliance. Let's go through the key points regarding the fire hydrant ring main, as specified in OISD 144, Chapters 11 and 12. First, the ring main for the fire hydrant system should generally be laid above ground. This ensures easy access and visibility for maintenance and operation. The pipeline should be installed at a height of approximately 300 to 400 millimeters above the finished ground level, which helps prevent damage and allows for easy inspection. Support is critical, so the mains need to be supported at regular intervals, not exceeding 6 meters, or as per the approved design. Proper support ensures stability and prevents undue stress on the piping. Additionally, the system for the above-ground portion must be analyzed for flexibility, especially against thermal expansion, to avoid stress and potential damage during temperature fluctuations. However, there are specific situations where laying the ring main underground is permitted. These include locations like road crossings, where above-ground piping could obstruct traffic or construction activities. Also, in areas where above-ground piping might hinder operational activities or vehicle movement, underground installation is preferred. Another important consideration is protection from mechanical damage. For example, in LPG storage areas, where water supply lines feed sprinkler or deluge systems, underground piping can prevent accidental damage. Frost conditions also play a role. If the ambient temperature is likely to fall below 0 degrees Celsius, the piping should be buried at least 1 meter below ground level to prevent freezing and ensure system reliability. In summary, while above-ground installation is generally preferred for ease of maintenance and inspection, strategic underground laying helps in specific circumstances to protect the system, ensure safety, and maintain operational efficiency. Let's now look at some key points from OISD 144, Chapters 11 and 12, specifically focusing on fire hydrant and water ring main requirements. First, in high-hazard areas, it's essential to ensure safety coverage. At least one hydrant post should be provided every 30 meters along the external wall measurement or perimeter of the battery limit. This spacing ensures quick access to water in case of a fire emergency. For non-hazardous areas, the spacing is a bit more relaxed, with hydrants spaced at 45 meters intervals. Importantly, when considering the horizontal range and coverage of hydrants with hose connections, we do not factor in beyond 45 meters. This helps in planning effective firefighting operations. Moving on to the fire water ring main, it must be sized to handle 120% of the design water flow rate. This additional capacity ensures reliability during peak demand. Also, The velocity of water within the ring main should not exceed 5 meters per second to prevent excessive pressure and pipe damage. When laying the fire-water ring main underground, there are specific provisions to consider. First, there should be at least a 1-meter earth cushion in open ground to protect the pipeline. Under road crossings, this cushion should be at least 1.2 meters deep, and for rail crossings, we must comply with Indian Railways' stipulated requirements. Protection against soil corrosion is critical, so the pipeline must be suitably protected. In cases where soil conditions are poor, we may need to provide concrete or masonry supports underneath the pipeline to ensure stability and integrity. These guidelines are all about ensuring the fire-water systems are reliable, durable, and effective in emergency situations, which ties into the overall theme of safety and preparedness in our designs. Now, let's look at some key safety features outlined in OISD 144, Chapters 11 and 12. First, at each hydrant point, a hose box with 2 hoses and a nozzle must be provided. This ensures quick access to firefighting equipment in an emergency. Next, when it comes to deluge valves, they should be located outside the curb wall, maintaining a safe distance, especially important in areas with LPG spheres or bullets. Specifically, they should be placed at least 15 meters away from the limits of LPG cylinder sheds to avoid potential hazards. A firewall is also recommended to protect the deluge valve and the operating personnel. This adds an extra layer of safety and containment. Regarding hydrants and monitors, they should be positioned at a minimum distance of 15 meters from tank wagons or trucks, measured from the edge of the facilities. Double-headed hydrants, equipped with 2 separate landing valves on a 3 or 4-inch standpost, are preferred. All hydrant outlets should be approximately 1.2 meters above ground level for easy access. Monitors are essential as well. They should be placed so they can direct water onto the fire object and provide a water shield for firemen approaching the fire. The placement of monitors should not exceed 45 meters from the hazard, ensuring effective water coverage. It's also important to note that hydrants and monitors should not be installed inside diked areas to prevent potential safety and operational issues. Finally, hydrants should be located at least 15 meters from the periphery of storage tanks or protected equipment. In the case of buildings, the distance should be between 2 and 15 meters from the building face, ensuring both safety and accessibility. All these measures collectively contribute to a comprehensive fire safety plan, ensuring effective firefighting capabilities while maintaining safety for personnel and facilities. Let's now look at some important guidelines from OISD 144, specifically Chapters 11 and 12, regarding sprinkler system design and maintenance. First, when projections such as manhole flanges, pipe flanges, staircase supports, or brackets obstruct the water spray coverage, we need to take additional measures. In these cases, extra nozzles should be installed around these projections to ensure the wetting pattern is maintained effectively. This helps prevent any gaps in coverage that could compromise fire protection. Next, in all critical areas, like LPG storage zones, sheds, LPG pump or compressor houses, tank truck or wagon loading and unloading zones, and valve manifolds, we must provide a medium velocity spray system. The purpose here is to ensure rapid and effective fire suppression in these high-risk zones. Additionally, the spray nozzles should be directed radially toward the vessel, and the maximum distance from the equipment surface should not exceed 0.6 meters. It's also important to note that within a single facility, only one type and size of spray nozzle should be used to ensure uniform performance and maintenance simplicity. Moving on to the markings, above-ground fire water mains and fire hydrant standposts should be painted with corrosion-resistant, fire-red paint, as per IS 5 standards. This helps in easy identification and longevity of the infrastructure. Similarly, water monitors, hydrant points, and hose boxes need to be painted luminous yellow, also following IS 5. This enhances visibility, especially during emergencies, ensuring quick access when needed. To sum up, these guidelines are all about ensuring reliable fire protection systems, proper coverage, and easy identification, which are all critical in safeguarding our facilities and personnel. Let's now discuss the key aspects of the automatic fire protection system outlined in this slide. Firstly, when we use quartzoid bulbs for fire detection, they are designed to blow at a maximum temperature of 79 degrees Celsius. This ensures quick response to rising temperatures. The QB network is maintained with plant air at a controlled pressure, not exceeding 3.5 kilograms per square centimeter. This setup is crucial because when one QB discharges, it depressurizes the system, triggering the deluge valves to activate. Once these valves are actuated, several safety measures kick in. An alarm is sounded at the control panel, LPG pumps and compressors are tripped to prevent further escalation, and any ROVs in LPG supply and return lines also trip off. Additionally, the fire water sprinkler system's deluge valves are activated to suppress the fire. In the LPG storage area, detectors are strategically placed around each vessel, ideally encircling them at a maximum spacing of 1 meter and positioned about 1.5 to 2 meters above the bottom of the vessel. To ensure redundancy and reliability, at least 2 detectors are installed at the top of each vessel, along with at least one near the liquid line ROV. This placement helps safeguard against potential failure of flanges or other critical points. Overall, these measures work together to provide a robust, automatic fire detection and suppression system, essential for maintaining safety in the plant. Now let's look at what happens when the detectors are actuated, according to OISD 144, Chapters 11 and 12. First, the deluge valves for the affected zone, as well as the adjacent zones, will open automatically. This helps to quickly control and suppress the fire spread. Next, an audio-visual alarm will activate at the fire pump house and the manned control panel, alerting personnel to the affected zone. The control panel also provides status indications for the deluge valves and includes a facility to manually actuate them if needed. In addition, a fire siren with a range of about 1 kilometer will sound off, ensuring that everyone in the vicinity is warned. Simultaneously, all remote-operated valves in the affected facility will close to contain the fire and prevent further damage. The main power supply to the facility will trip, except for emergency power, to isolate electrical sources and reduce risks. Within just 30 seconds, water spray will be released from all nozzles, providing immediate suppression around the affected area. Finally, the fire water pumps will start up based on their set pressure thresholds, helping to maintain the water pressure in the ring main and support ongoing fire suppression efforts. All of these actions work together seamlessly to ensure a rapid, coordinated response to fire detection, minimizing damage and protecting personnel. Let's go through the details of the portable fire extinguishers as outlined in OISD 144, Chapters 11 and 12. Starting with the LPG storage vessels, there should be 2 10 kg DCP extinguishers available nearby to quickly respond in case of a fire. Next, the LPG cylinder sheds require 2 10 kg DCP extinguishers for every 200 square meters of area. This ensures adequate coverage and safety in those zones. In the LPG pump houses, you'll find 2 10 kg DCP extinguishers designated for every 50 square meters of area. This placement helps address potential fire hazards associated with pumping operations. For tank truck loading and unloading gantries, each bay should be equipped with a 10 kg DCP extinguisher. Similarly, tank wagon loading and unloading gantries should have 1 10 kg DCP extinguisher for every 15 to 20 meters of gantry length, ensuring sufficient firefighting capability along the entire area. Other pump houses are also provided with 2 10 kg DCP extinguishers for quick access. In office, canteen, and stores buildings, there should be two 10 kg DCP extinguishers in each structure, catering to indoor safety requirements. In the PMCC, DG room, and HT room, we need two CO2 extinguishers of 4.5 kg each, covering about 100 square meters per room. Additionally, 4 sand buckets on a stand should be provided in the MCC and DG rooms for quick access to sand in case of electrical or flammable liquid fires. Now, moving to first aid firefighting equipment, it's crucial to have portable fire extinguishers readily accessible throughout these key areas. These extinguishers are vital for initial response and controlling small fires before they escalate. Ensuring these placements and quantities align with standards is essential for safety and effective firefighting. Remember, quick access and proper distribution of firefighting equipment can make all the difference in emergency situations. Now, let's talk about the hoses and nozzles as outlined in OISD 144, Chapters 11 and 12. First, we need to ensure that the hoses used are reinforced rubber-lined hoses with a diameter of 63 millimeters, conforming to IS 636. Either type A or B, these hoses should be standard 15-meter lengths and equipped with gunmetal or aluminium alloy male and female couplings of the instantaneous pattern for quick and secure connection. It's also important to note that we need to have a minimum of 2 hoses, or at least 25% of the total hoses, stored as spare in the LPG plant. This ensures quick replacement in case of damage or wear during operations. Additionally, beyond the hoses provided in the hose boxes, we must keep at least 2 spare nozzles in each category. These categories include jet nozzles with branch pipes, fog nozzles, universal nozzles, water curtain nozzles, spray nozzles, and triple-purpose nozzles. This gives us flexibility and readiness for various firefighting scenarios. Moving on to fire extinguishers, specifically the 75 kg DCP mobile fire extinguisher, we need to place one in key areas such as the filling shed, LPG storage vessels, LPG pump house, and both the tank truck and tank wagon loading and unloading gantry areas. These locations are critical points where fire risks are highest, so having such extinguishers readily available is essential for safety. Overall, these provisions for hoses, nozzles, and fire extinguishers are designed to ensure we have effective firefighting measures in place, minimizing risks and enhancing safety across the plant. On this slide, we're looking at the accessories and first aid items that must be provided within the plant, as per OISD 144, Chapters 11 and 12. First up, we have fire hoses. It's essential to have 2 hoses for each hose box to ensure quick access and adequate coverage during emergencies. Next, safety helmets are mandatory for all personnel. Each person should have one, with a minimum of 10 helmets available. This helps protect everyone from head injuries. Hose boxes should be strategically placed at each hydrant point, making sure firefighting equipment is always within reach. For medical emergencies, a stretcher with at least 2 blankets should be available to assist injured personnel efficiently. Additionally, there should be at least 2 first aid boxes stocked and ready for use at different points in the plant. In terms of personal protective equipment, rubber hand gloves are a must, at least 2 pairs, BIS approved, especially for electrical work. For LPG emergencies, we need low-temperature rubber gloves, 4 pairs, as specified in OISD GDN 115, designed to handle the specific hazards involved. Similarly, low-temperature protective clothing for LPG emergencies should be available, with at least 2 sets on hand. This gear is critical to ensure safety during LPG-related incidents. A fire proximity suit is also vital. Having at least one ensures that personnel can safely operate close to high-temperature flames or hot surfaces. Resuscitators are important too. At least 2 should be kept available for emergency medical response, helping with immediate life support if needed. Lastly, red and green flags should be provided as required, mainly for signaling or communication during emergency situations. All these accessories and first aid items collectively play a crucial role in maintaining safety and preparedness in our plant environment. Now, let's move on to some critical safety equipment as outlined in OISD 144, Chapters 11 and 12. First, we have the self-contained breathing apparatus, or SCBA. It's essential to have at least one unit available, along with a spare cylinder. The capacity of these units is typically around 30 minutes, which is crucial for ensuring safety during emergency situations. Next, we look at water gel blankets. Having at least 2 of these on hand is vital. They are effective for fire suppression and cooling, especially in hazardous environments. Finally, portable gas detectors or explosimeters are equally important. At least 2 of these devices should be available to monitor the atmosphere for any presence of hazardous gases or potential explosions. All these items are part of our overall safety strategy to protect personnel and control risks effectively. They ensure that in an emergency, we're prepared with the right tools to respond swiftly and safely. Let's go through some key points about the fire alarm system as per OISD 144, Chapters 11 and 12. First, manual call points should be installed near critical areas such as the filling shed, storage area, tank truck or wagon gantry, and pump house. These points must be clearly marked to ensure quick identification during an emergency. When someone operates these call points, they should trigger an audio-visual alarm in the control room, alerting the team immediately. Next, the fire siren system is crucial. An electrically operated fire siren should be loud enough to be heard up to 1 kilometer from the plant's periphery, ensuring that even those at the farthest points are alerted. Additionally, manually operated fire sirens should be strategically placed around the site for quick access and response. Regarding the siren signals, a fire condition is indicated by a wailing sound that lasts at least 2 minutes. When the situation is under control or all clear, the siren should run straight for 2 minutes. In case of a disaster, the wailing sound is repeated 3 times with a minimum 10-second gap between each cycle, emphasizing the seriousness of the situation. These measures, when implemented properly, create a reliable warning system that can save lives and protect property by ensuring swift and clear communication during emergencies. Let's go over the key points related to fire water pumps as per OISD 144, Chapters 11 and 12. First, every pump must undergo a test run at least twice a week for a minimum of 10 minutes each time, and this should be done at the rated conditions. This regular testing ensures the pumps are functioning properly and can deliver the required pressure during an emergency. Additionally, once a month, each pump needs to be checked and tested thoroughly. During this check, the shutoff pressure should be observed carefully and logged for records. This helps us monitor the pump's performance over time and identify any potential issues early. Now, moving on to the jockey pump, it's essential to periodically verify its operation. If we notice frequent start and stop cycles, it usually indicates there could be water leaks within the system. Detecting and addressing these leaks promptly is critical to maintaining system integrity and readiness. Let's talk about the fire water ring main. The ring main should be kept pressurized at around 7 kg per square centimeter gauge, which is maintained by 1 or more jockey pumps. Keeping it pressurized ensures immediate availability of water during an emergency. Inspection of the ring main is also vital. At least once a week, we need to visually check for leaks, damages, or corrosion and maintain proper records of these inspections. This proactive approach helps us ensure the system remains in optimal condition. Finally, all valves connected to the ring main, hydrants, and monitors should be checked once a month. We need to verify they operate correctly, check for leaks, and lubricate them as necessary. Proper maintenance of valves guarantees they function correctly when needed most. In essence, these practices, regular testing, inspections, and maintenance, are fundamental to ensuring the fire water system remains reliable and ready to protect lives and property. Now, let's discuss the requirements for the fire water reservoir as per OISD 144, Chapters 11 and 12. It's important to note that the reservoir must be cleaned at least once every 6 months, or even earlier if needed. This helps prevent the buildup of foreign particles, fungi, or vegetation that could compromise the water quality or system functionality. Regular cleaning ensures the reservoir remains in optimal condition for fire safety. Moving on to the fire water sprinkler system, there are a few key points to keep in mind. First, all deluge valves and the sprinkler system should be operated and checked quarterly. This routine check ensures that each nozzle is functioning correctly and that the entire system is effective when needed. It's vital to verify remote operation performance so that in an emergency, the system responds promptly. Additionally, testing the sprinkler system in the sheds involves closing the outlet of the deluge valve quarterly. This simulates actual activation conditions and confirms that the system will operate correctly during a fire. Lastly, the strainers installed in the sprinkler system need to be cleaned once every quarter as well. Keeping these strainers clean is crucial because they prevent debris from clogging the nozzles and disrupting water flow. And of course, record keeping of these maintenance activities is essential for accountability and future reference. All these measures, from cleaning the reservoir to quarterly testing and maintenance, are part of our overall fire safety strategy. They ensure that our fire protection systems remain reliable and ready to perform when needed. Now, let's look at slide 21 from our presentation on OISD 144, specifically chapters 11 and 12. Here, we're focusing on the most hazardous scenario that can occur with LPG vessels, which is a BLEVE, a boiling liquid expanding vapor explosion. This situation typically happens when the vessel is exposed to an external fire. When a fire heats the vessel, the unwetted, or vapor space, portion of the shell gets overheated. Even if the vessel is operating at a certain pressure, this overheated metal can fail, leading to catastrophic consequences. That's why it's crucial to protect the metal temperature in the vapor space from overheating. One effective way to do this is through passive measures, such as fireproofing, insulation, or fire retardant coatings. These protective layers act as a barrier, providing crucial initial protection during the early stages of a fire. This initial period is extremely important because it allows us vital time to activate other firefighting measures, like starting pumps, organizing personnel, or opening valves. Additionally, these passive measures help safeguard automated systems, ensuring that safety mechanisms continue to operate even if manual intervention is delayed. In summary, implementing these fire protection strategies is essential. They buy us critical breathing space, reduce the risk of vessel failure, and help prevent a BLEVE. This is a key aspect of overall safety management for LPG storage and handling. Let's review some key points from OISD 144, specifically chapters 11 and 12. Fireproofing must include the connected LPG lines and pipe supports that are within 15 meters of a storage vessel or along the drainage paths. This is crucial to ensure safety in case of a fire, especially near LPG storage areas. Additionally, the routing of fire water lines to each sphere should be carefully planned. They should be positioned so that they are not exposed to direct fire. This helps protect the water supply system from failure during the critical initial moments of a fire, when water flow is most needed. Another important aspect is the placement of risers. It's recommended that risers be located away from the bottom ROV or remote operating vehicle. This minimizes risk and helps maintain operational safety. Now, regarding fireproofing ratings, the minimum standards are quite specific. For LPG storage vessels and the connected lines up to the fire-safe ROVs, a fire resistance of at least 1 hour is required. For the supporting legs of all these components, a minimum rating of 2 hours is recommended. These measures are vital for overall safety and integrity of the system, aligning with our broader goal of ensuring safety and reliability in our operations. Now, let's discuss the key considerations for the location of detectors as outlined in OISD 144, Chapter 11 and 12. First, The behavior of gas leakage is crucial in determining where to place the detectors. Since LPG is heavier than air, it's important that the detector is not mounted too high. Ideally, it should be within 0.3 meters from the mounting level to effectively sense the gas. Next, we need to consider the prevailing wind direction. Positioning the detector on the downstream side of the potential leak source allows us to catch the gas before it disperses further. This ensures early detection and enhances safety. Additionally, for catalytic-type detectors, placement is key. They should not be placed too close to potential leak points because proximity can lead to poisoning of the sensor, which causes temporary malfunctioning. A safe distance of at least 0.3 meters from the leak source is recommended to prevent this issue. Moving beyond placement, the gas monitoring system as a whole must be capable of providing early warnings, especially for small leaks. These include leaks from mechanical seals, open sampling points, gasket failures, hose pinholes, valve gland leaks, partially open drain points, relief discharge points in the manifold, and leaks from filling or evacuation hoses. In essence, the system should be sensitive enough to detect the buildup of gas concentrations below the lower flammability limit, giving us enough time to respond before a dangerous situation develops. By considering all these factors, gas behavior, wind direction, detector placement, and system sensitivity, we can ensure a safer environment and effective leak detection. Now, moving on to the specifics of infrared detectors as outlined in OISD 144, Chapter 11 and 12. It's important to install these detectors on the downwind side of the installation. This ensures that if there's any gas release, the detectors are positioned to effectively sense the gas as it drifts downwind. Additionally, the path must be clear of obstructions to maintain unobstructed gas detection. If any expansion or new construction occurs later, the detectors should be pre-positioned accordingly to maintain safety coverage. Next, let's look at the minimum detector requirements based on facility types. For storage vessels above ground, we need at least 2 detectors, one at the top and one near the bottom riser outlet valve. In the LPG pump house, detectors should be placed inside the pump house itself and at the manifold. The filled cylinder shed requires 2 detectors, ensuring coverage for potential leaks. The valve change shed should have at least 1 detector, while the empty cum filling shed needs more, 2 near the carousel, 1 near the evacuation unit tank, and 1 at the weight correction unit. Regarding tank wagon gantries, the standard is 1 detector for every 2 bays or every 30 meters, whichever is less, positioned at the bottom. Additionally, some detectors should be installed at strategic locations at the top of the platform to enhance detection coverage. Finally, the placement of these detectors isn't arbitrary. It should be decided based on assessing how gas behaves, specifically, how it drifts, and the associated safety risks. By understanding gas behavior, we can optimize detector placement to ensure early detection and mitigate risks effectively. This approach aligns with our overall goal of ensuring a safe and secure facility. Let's talk about the importance of monitoring the drift in the sensitivity of our detectors. As per OISD 144, Chapters 11 and 12, we need to record any changes in the sensitivity of each detector in the maintenance history log during calibration. This helps us keep track of their performance over time. If a detector shows abnormal or wide drift in sensitivity, it indicates it might not be reliable anymore, and we need to address that promptly. It's also crucial to have at least 2 spare detectors for each system on site at all times. This way, if a detector becomes defective, we can replace it immediately without any delay, ensuring continuous safety coverage. Now, regarding inspection, the system should be checked every month. During this inspection, we release gas at all detectors to verify they are responding correctly and that the system is functioning as intended. This regular testing is vital because it confirms the system's operational integrity and helps us catch potential issues early. Overall, these procedures, tracking drift, maintaining spares, and monthly testing, are all about ensuring our gas detection systems remain reliable and effective in safeguarding the plant. Thank you all for your patience throughout this presentation. Now, let's end on a fun note. Can you guess who the billionaire is here? It's a playful way to remind us that sharing knowledge truly makes us richer. Remember, when we share what we know, we don't just help others, we also grow ourselves exponentially. In fact, you earn 1,000,000,000 times over when you contribute to the collective knowledge. So always be open to sharing and learning from others. It's this spirit that drives innovation and success, both in our personal and professional lives. Thank you once again for your attention, and I hope you found this session insightful and inspiring.